When people in the US hear "the last frontier," the mental picture usually goes straight to space, rockets, the moon, Mars, and that makes total cultural sense. But if we're being honest as historians of science and as Earth systems people, that phrase also belongs to a place we've lived next to forever and still don't fully see: the deep ocean. The ocean covers about 71% of Earth's surface, and that number is familiar enough that it almost stops sounding dramatic, but it should still hit us every time, because it means most of our planet is a realm where humans don't naturally survive and don't easily observe. Most of the ocean is deep, cold, dark, and under pressure that changes the rules of biology and engineering. The average depth of the global ocean is roughly 3.7 kilometers, which already dwarfs most of what we casually imagine when we say the sea. And then the Mariana Trench takes that baseline and pushes it into genuinely extreme territory. This trench lies in the western Pacific near the Mariana Islands, and it's the deepest known trench on Earth. Its length is on the order of about 2,500 kilometers, and within it sits a name you'll hear again and again in exploration history: Challenger Deep. The depth of Challenger Deep, measured with modern instruments that are far better than the old rope and weight methods, is about 10.9 kilometers, give or take a little depending on the specific survey. The exact number has been refined over time, but the big truth is stable. This is the deepest confirmed point in the global ocean. For scale that a lecture audience can feel, Mount Everest is about 8.8 kilometers high. So if you could drop Everest into Challenger Deep, the summit would still be more than 2 kilometers underwater. That's not a fun fact for trivia night. That's a way to anchor how far outside normal human experience this environment really is. Now, if you're using this video to fall asleep, that's exactly why I make these. So maybe subscribe and tell me where you're watching from and what time it is. I always check the comments, and it's fascinating seeing Sydney at breakfast and Lisbon at bedtime. All at once, all of us wondering about the same mysteries. Why does this matter in a history format lecture instead of just a geology class? Because the trench is not only a place on a map, it's a case study in how knowledge gets made. For centuries, the ocean was a surface world in human imagination. People sailed it, traded across it, fought on it, feared it. But the deep, below the reach of light, was mostly a conceptual void. That void got filled with stories, because stories are what humans do when instruments can't reach. So we had myths of monsters, bottomless pits, a kind of symbolic underworld. But the modern scientific story of the Mariana Trench is about the long, slow transition from imagination to measurement. This transition doesn't happen in one heroic moment. It happens when someone funds a voyage, when engineers improve tools, when governments decide the data are worth the cost, and when scientists argue, sometimes loudly, about what the measurements even mean. The trench is also a reminder that exploration doesn't always mean discovering a new continent. Sometimes it means discovering a new set of conditions on a planet we already thought we understood, which quietly messes with the tidy story we like to tell about progress. We often summarize modern history as if humanity wrapped up Earth and then moved on to space. But the truth is more uneven. We explored parts of Earth intensely, especially where the payoff was obvious in resources, navigation, or geopolitics, while huge regions of the deep ocean stayed remote, not because we didn't care at all, but because keeping machines and humans alive down there is brutally hard and expensive. So the ocean's forgottenness is not ignorance in a simple sense. It's a choice shaped by technology, budgets, and attention. When the U.S. created the Mariana Trench Marine National Monument in 2009, that was an official acknowledgement that this isn't just a dramatic abyss for documentaries, it's a scientific and ecological system worthy of protection and long-term study. That policy move matters for our narrative because it shows how deep ocean knowledge is no longer just about daring dives, it's also about stewardship and competing futures. And we'll get to those futures later. For now, the key idea you can carry into the rest of this lecture series is simple. The Mariana Trench is a boundary zone where Earth shows its most extreme ocean conditions, and it's a powerful reminder that the unknown isn't only above us, it's under us, very close in distance, very far in physics. As we move into the next chapter, we'll stop speaking in broad frames and start talking about the most direct physical reality of this place: pressure. The trench is not scary because it's dark in a poetic way. It's scary because the water column above you turns into a crushing force that breaks steel, bends glass, and challenges every assumption we make about where life can exist. That's where the story gets more intense, more specific, and honestly, more fascinating. Let's talk about the thing that makes the Mariana Trench feel less like deep ocean and more like a different planet. Pressure, plain and simple. The phrase "hell on Earth" is obviously a rhetorical flourish, but it points to a real idea that scientists and engineers keep running into down there. The environment is so physically hostile that almost everything we build for the surface fails unless we redesign it from scratch. Pressure is not just a number on a chart, it's a force that changes what materials can do, what organisms can survive, and what times of exploration are even possible. Here's the basic rule of thumb that's easy to remember in a lecture. In seawater, pressure increases by about 1 atmosphere for every 10 meters of depth. The exact conversion depends on water density and local conditions, but as a teaching scale, it's solid. So when you're talking about Challenger Deep, around 10.9 kilometers down, you're in the neighborhood of roughly 1,100 atmospheres of pressure. In scientific units, that's around 110 megapascals. If you want the US audience version, that's on the order of 16,000 pounds per square inch, pressing on every exposed surface. It's difficult to make that intuitive because humans don't live with anything close to that. We're not built for it, and neither is most of our technology. This is why early deep-sea exploration was so slow to develop. Curiosity alone doesn't get you past physics. Pressure does a few nasty things at once. First, it tries to crush any space that contains air, which is why submersibles that carry humans rely on thick, high-strength pressure spheres, often titanium today and specialized steels earlier. Second, it exposes weak seals, flawed welds, micro cracks, and design assumptions that are harmless at shallow depths. Third, it makes failure catastrophic. An implosion at extreme depth is not a gentle accident. It's sudden and violent, driven by that gigantic pressure differential. So the engineering philosophy for Hadal exploration, the Hadal zone being roughly 6,000 to 11,000 meters deep, is conservative by necessity. You minimize points of failure, you obsess over geometry, you test materials, you use redundant systems, and you accept that every dive is a controlled risk. Now add the other environmental features that pile on to the stress. Temperature in the deepest trench waters is near freezing, generally around 1 to 4 degrees Celsius. There is no sunlight at all, and that matters not just for mood, but for ecology. On the surface, we associate life with photosynthesis. In the deep, life has to rely on organic matter drifting down from above, occasional big food falls like dead whales, or chemical energy sources in certain geological settings. But even before we get into biology, just sit with the physical reality. It's dark, cold, and crushing. If space is vacuum and radiation, the trench is weight and water and silence punctuated by mechanical stress. Two extremes, two different kinds of hostility. A common misunderstanding is that the Mariana Trench is uniformly the same conditions across its entire length, like a single vertical shaft. It's not. It's a complex geological structure formed by subduction, where the Pacific Plate is forced beneath the Philippine Sea Plate. That movement bends and fractures Earth's crust, creating a long, deep trough with variations in depth, slope, and sediment. So the pressure environment is extreme across the Hadal floor, but it's not one flat number everywhere. This matters because modern mapping and targeted sampling have shown that even small changes in topography can influence what kinds of sediments accumulate and how organisms distribute themselves. In other words, this isn't just the deepest place, it's a connected system with microenvironments that researchers are still trying to understand. What does pressure do to life? This is where the story often gets simplified into something like, nothing can live there. And that's wrong. Life exists in the trench, including microbes, crustaceans, and fish in surrounding Hadal regions. But the key is that life at these depths is specialized. The proteins, cell membranes, and biochemical pathways have to function under high pressure. The bodies of Hadal animals are generally adapted to avoid large gas-filled spaces and to maintain cellular function through pressure-tolerant chemistry. That's a preview of later chapters, but it's worth mentioning here because it flips the emotional tone. The trench is not a dead zone. It's a selective zone. The conditions don't eliminate life, they filter for a narrow set of adaptations. That's a more accurate and more interesting scientific idea. From a historical perspective, pressure is also the invisible antagonist in every exploration chapter we're going to cover. The early sounding expeditions in the 19th century were limited not just by navigation and weather, but by the difficulty of getting accurate measurements under conditions where cables stretch and currents drift and instruments behave unpredictably. Later, when we get to the 20th century, pressure is the reason deep diving vehicles were rare, expensive, and often politically tied to national prestige or military interest. It's also a reason for long gaps in human presence down there. When you need a custom-built machine for a single dive profile, you don't casually schedule a weekly trip to the bottom of the world. So, in a very real sense, the Mariana Trench is hell not as a supernatural metaphor, but as a practical description of the environment's resistance to intrusion. It pushes back against our materials, our budgets, and our patience. There's also a subtle conceptual angle that's useful for a lecture audience. Pressure is a reminder that depth is not just distance. On land, we think in miles. In the ocean, each additional kilometer downward is a step into a new physical regime. And at some point, the regime becomes so extreme that you can't treat it as an extension of the shallow sea. You have to treat it as its own world. That mental shift is exactly what the history of oceanography had to go through, from surface exploration to deep-sea science. So if you want a clean way to end this chapter in your spoken delivery, you can land on this idea. The Mariana Trench is not terrifying because it is far away. It is terrifying because the physics down there are simply not negotiable. Pressure is the gatekeeper. Everything we learn about the trench, its geology, its biology, its role in Earth systems, depends on whether we can build tools that survive the squeeze. And that is why the next chapters about early measurement, the HMS Challenger, and the later era of deep submersibles are not side stories. They are the human response to a planet that still has places where the environment is stronger than our assumptions. If Chapter 2 was about the physics that blocks us, this one is about the moment humans started to measure that block with real seriousness. The story of the Mariana Trench in modern science really begins with a ship that wasn't built for deep ocean fame at all. HMS Challenger was a Royal Navy corvette repurposed for science, and between 1872 and 1876, it carried out what is often described as the first global oceanographic expedition in the modern sense. The significance is hard to overstate without getting melodramatic, so I'll put it plainly. This voyage helped transform the ocean from a blank on the map into a physical system that could be measured, categorized, argued over, and slowly understood. Before Challenger, people had made depth measurements, sure, but there wasn't a coordinated, wide-ranging, data-driven program that treated the ocean as a world with structure from surface to seafloor. Challenger changed that culture. The ship sailed a vast route around the globe, stopping to take soundings, measure temperatures, collect water samples, dredge for organisms, and record seafloor sediments. It was slow work, it was repetitive work, and it was revolutionary work. Now, in 1875, during this expedition, Challenger took the first measurements in the region that would later be associated with the deepest part of the Mariana system. Using a weighted sounding line, the crew recorded a depth of around 4,475 fathoms in the western Pacific. Converted, that's roughly 8.1 kilometers. That number is not the true maximum depth of the trench as we understand it today, but that's the point. The tools of the era could not easily measure the full extreme. What they could do was show unmistakably that the ocean contained depths far beyond what many people had comfortably imagined. The reading was shocking for its time. It suggested that Earth had a kind of submerged topography on a scale comparable to mountain ranges on land, except inverted. And even though the exact deepest point would be refined much later with echo sounding and then modern high-precision surveys, the Challenger measurement became historically foundational. That's why the name Challenger Deep eventually stuck for the deepest known point in the global ocean. It honors not just the ship, but the turning point in method and mindset. This is a good place to zoom out for your audience and emphasize what measurement meant in the 19th century. Today, we think of depth data as something that appears on a screen. For Challenger, it was a physical confrontation with the ocean. Lines could drift with currents, cables could stretch, weights could behave unpredictably. The deeper you went, the more potential error you introduced. So the achievement wasn't perfect accuracy by modern standards. The achievement was the act of building a disciplined approach to a hostile environment and recording results systematically enough that later generations could improve upon them. That's a major theme in the history of science. The first big step is often not getting the final answer, but proving the question is measurable. Challenger also carried a broader message that fits nicely into a lecture structure. It wasn't just a depth mission, it was one of the earliest large-scale attempts to link physical oceanography with biology and geology. When the crew dredged organisms from deep water and analyzed sediments, they contributed to the slow collapse of the old assumption that the deep sea was universally lifeless. That debate was already underway in the 19th century, and Challenger supplied evidence that helped move the scientific consensus toward the idea that life, in some form, existed far deeper than previously accepted. So in a single expedition, you have multiple revolutions: mapping, sampling, classification, and the emergence of the ocean as a legitimate three-dimensional scientific subject. In a history lecture for a U.S. audience, you can also point out the institutional context. This was an era when empires and navies funded science partly because knowledge was power. Better understanding of the oceans had practical value for navigation and national prestige. Challenger sits in that intersection of curiosity and state capacity. It shows how expensive, ambitious science usually needs infrastructure, and how the story of discovery is often inseparable from the story of who had ships, who had funding, and who had the political will to send a vessel around the world for years. When you're speaking this chapter out loud, I'd recommend framing Challenger as the opening of a long conversation rather than a single heroic discovery moment. The trench wasn't fully revealed in 1875, but the intellectual door was opened. The ocean floor was no longer an abstract idea. It was a measurable landscape with extremes that demanded new theories and better tools. And that sets us up perfectly for the next chapter, where we move from the era of measurement by line and weight to the deeper geological explanation, how colliding tectonic plates carved an abyss that makes these numbers possible in the first place. If we strip away the drama and just ask the blunt scientific question, why is the Mariana Trench there at all? The answer is plate tectonics, specifically subduction, which is one of the most powerful engines shaping the modern Earth. The Mariana Trench exists because the Pacific Plate is being forced beneath the Philippine Sea Plate along a long, curving boundary in the Western Pacific. And this is not a gentle overlap, it's a slow, relentless mechanical process where cold, dense oceanic lithosphere sinks into the mantle. Over geologic time, that descent bends the seafloor downward, creates a deep trench at the surface, and links the ocean's deepest landscape to Earth's internal heat and motion. This is part of the larger Isu-Bonin-Mariana system, a connected arc trench complex that formed as the Western Pacific reorganized and new subduction zones developed. So the trench is not an isolated whole, it is one surface expression of an entire subduction machine. You can picture the basic geometry like this. An oceanic plate approaches the boundary, starts to flex, and then dives, producing an outer rise seaward of the trench and a sharp drop where the plate begins its descent. The bending creates fractures and faulting in the incoming plate, which matters because those cracks can allow seawater to penetrate deeper into the crust and upper mantle. That water doesn't just sit there. It gets carried downward with the subducting slab, and at depth, It helps trigger melting in the mantle wedge above the sinking plate. That melt feeds the volcanic arc, the chain of islands and submarine volcanoes that runs roughly parallel to the trench. So we have a three-part story: trench, volcanic arc, and behind the arc, in this case a back arc region known as the Mariana Trough, where extension and spreading have occurred. The same subduction dynamics that create a deep trench can also produce back arc opening, because the system evolves not only by pushing plates together, but by complex rollback and stretching in the overriding plate. That two-direction feel, compression here, extension there, is one of the reasons the Mariana region is such a favorite natural laboratory for geologists. It's complicated in a productive way. Now, why does Mariana get so deep compared with many other trenches? In simple terms, very deep trenches are often associated with subducting plates that are old, cold, and therefore dense enough to sink steeply and effectively. The Pacific Plate in this region is among the oldest oceanic lithosphere on Earth, and that age-energy density relationship helps explain why the system can generate such extreme bathymetry. But don't oversimplify this in your delivery. Depth is not controlled by one variable. It's a multi-factor output of plate age, convergence geometry, sediment supply, the mechanical strength of plates, and the evolving shape of the subduction zone itself. The Mariana Trench is relatively low in sediment compared with some other subduction zones, and that can help preserve sharp, deep trench morphology, rather than filling it in with thick accumulations. The seafloor here is not just being pushed down, it is also not being rapidly smoothed over. Another thing worth stressing is that this is an active tectonic environment. Active doesn't necessarily mean constant disaster for nearby populations in the same way some continental collision zones do, but it does mean the region produces earthquakes and volcanism as part of normal subduction behavior. Those events are signals of stress release and mantle dynamics, and they remind us that the trench is a living boundary in Earth terms, not a fossilized relic. So when we talk about Challenger Deep and the extreme depths, we should quietly remember we are looking at the surface fingerprint of forces operating tens to hundreds of kilometers below, where rock flows over time, where chemistry changes, where water alters minerals, and where heat builds new crust in one place while old crust disappears in another. This is also where the trench becomes relevant beyond pure geology. Subduction zones are central to Earth's long-term carbon cycle and volatile recycling. Material from the surface, sediments, altered oceanic crust, water-bearing minerals, gets transported downward, transformed, and in some cases returned to the surface through volcanic gases and eruptions. So the Mariana Trench is part of the planet's deep recycling system. It helps regulate, on long timescales, what Earth's atmosphere and oceans can be. That's a big statement, but it's not a mystical one. It's a system statement. In a lecture, this chapter is your chance to shift the audience from "wow deep" to "okay, this depth has a cause, and that cause connects to the whole planet." The trench is not just a record holder, it is evidence that Earth is dynamic from crust to mantle, and that the ocean floor is not a static basin, but a moving, renewing surface. And that sets up the next chapter nicely, because once you understand the trench as a tectonic product, you can start asking new questions about its environment, like why it may be surprisingly noisy for such a remote place, and what that tells us about geology, biology, and even human activity. When people imagine the bottom of the Mariana Trench, they usually picture total silence, like a black, frozen vacuum. That expectation makes emotional sense. No light, almost no human presence, miles of water overhead. But acoustically, the deep ocean doesn't work like our instincts. Water is an excellent medium for sound, especially low-frequency sound, and the ocean is stitched together by physics in a way that lets noise travel astonishing distances. So the honest scientific headline here is not that Challenger Deep is literally the single noisiest place on Earth in some simple ranking. It's that it is surprisingly loud for how remote it feels, and it's loud for reasons that are both local and planetary. Start with the basic mechanics. Sound speed in seawater depends on temperature, salinity, and pressure. Near the surface, warm water helps sound move faster. As you go down, temperature drops, so sound speed decreases. But keep going deeper, and pressure becomes the dominant factor, pushing sound speed back up. That layered structure creates pathways where certain sounds can travel far without losing much energy. The most famous is the Deep Sound Channel, often called the SOFR channel, typically around the mid-depth ocean where sound speed hits a minimum. A sound wave that enters that channel tends to refract back toward the center of it, traveling long distances like it's on a hidden highway. The Mariana Trench sits far below this, but the effect still matters for the story because it means the deep ocean can hear the wider planet. The trench is not a sealed cave. It's more like a very deep listening post connected to an enormous watery acoustic network. So what is it hearing? First, Earth itself. The Mariana region is an active subduction zone, and earthquakes are part of that tectonic reality. When the seafloor shakes, it doesn't only send seismic waves through rock, it can also generate acoustic signals in the water. Add to that the possibility of submarine landslides, sediment shifts, and smaller-scale fracturing events. The trench is a place where the crust is under stress, so the soundscape includes the audible fingerprints of a planet that is still moving. Second, the weather above the ocean. Big storms generate low-frequency noise that can propagate downward and outward. The deep sea receives a kind of distant rumble from surface chaos. Even when the surface is calm locally, the ocean basin is wide enough that something is always happening somewhere. That means deep hydrophones can pick up signatures of weather systems far from the trench itself. Third, biology, though not in the cute, near-shore sense people usually expect. Large marine animals, like whales, don't dive to Challenger Deep, but their calls can travel through the ocean and be detected at very great depths. The trench can be a passive receiver of life activity happening higher in the water column or in surrounding regions. So the deep doesn't have to be packed with sound-making organisms to have a rich biological layer in its audio environment. Fourth, us. This is where the story gets uncomfortable, because even the most remote ocean spaces are not acoustically isolated from human civilization. Global shipping produces a lot of low-frequency sound that can travel across basins. So the Mariana Trench may be far from dense shipping lanes compared with other regions, but it is not immune to the broader ocean-wide increase in anthropogenic noise. That's a quiet consequence of globalization. We change the soundscape of places we never see. And if you're thinking ahead in your lecture, yes, this also overlaps with Cold War and post-Cold War military technologies, but I'd save most of that for the later chapter where it belongs, so this part doesn't turn into a detour. The historical punchline here is that the idea of a silent abyss is partly a product of earlier technological limits. If the only way you can interact with the deep sea is by throwing a line overboard and hoping for clean measurements, you don't develop a sensory picture of the trench as a living, dynamic environment. But as instruments improved, especially with long-term hydrophone deployments and deep-sea landers, scientists started to realize that the Hadal world has its own acoustic personality. And that realization matters beyond curiosity. Sound is data. It can be a way to monitor earthquakes, to study animal presence indirectly, to understand how storms echo through an ocean basin, and to track the growing footprint of human activity. In other words, the trench is not just deep space underwater. It is part of a noisy, active Earth system that carries information in waves we can record, even when we can't always visit in person. So if you want a clean, memorable way to close this chapter when you're speaking, try something like this. The Mariana Trench looks like the ultimate isolation chamber, but it doesn't behave that way. Geology, weather, life, and human industry all leave acoustic traces, and the deep ocean collects them. The abyss is not quiet, it's attentive. If the HMS Challenger chapter was about measuring the abyss from the surface, the Trieste is where that abyss finally gets a human presence inside it. Not metaphorical presence, not we dropped an instrument, but two actual people in a pressure sphere going down to the deepest known point in the ocean. On January 23, 1960, Jacques Piccard and U.S. Navy Lieutenant Don Walsh took the bathyscaphe Trieste to the bottom of Challenger Deep. The depth they reported at the time was about 35,800 feet, roughly 10,916 meters. And modern measurements have refined the exact number, but the historical fact that matters is simple. This was the first confirmed crewed visit to the deepest part of Earth's ocean. The Trieste itself is a perfect Cold War-era hybrid of ambition and improvisation. It was originally designed by Auguste Piccard, Jacques' father, built in Italy with support connected to Swiss-Italian engineering, and later purchased by the U.S. Navy. It was modified for extreme depth work, including a strengthened pressure sphere. This is worth emphasizing in a history lecture because it shows how deep ocean exploration wasn't just a heroic adventure story. It was also a story of institutions, military interest, and the kind of funding that only big national priorities could release. The vehicle's design was unusual by everyday standards, but logical for the physics. A heavy, compact crewsphere attached to a huge float filled with gasoline, because gasoline is less dense than seawater and relatively incompressible compared with air. That buoyancy concept was essential. You can't brute force your way down there with normal submarines. The descent took hours. Contemporary accounts describe the trip downward as long, quiet, almost tedious in rhythm until something goes wrong or almost goes wrong. And here we get the famous detail that you'll want to deliver carefully so it doesn't turn into legend instead of history. During the descent, one of the observation window components cracked. Most retellings describe it as an outer acrylic layer rather than a catastrophic failure of the main pressure boundary, and the crew decided to continue, which tells you two things at once. First, how confident they were in the overall engineering, and second, how high the tolerance for risk was in this era of exploration. They reached the bottom and stayed briefly, often reported as around 20 minutes of bottom time, before beginning the long ascent. The point for your audience is not the exact minute count, though you can mention it to give texture. The point is the human experience of this environment. Extreme pressure, near freezing temperatures, absolute darkness outside the lights, and the awareness that you are sitting inside a small engineered bubble that must not fail. Historically, the Trieste dive became iconic in a way that deep ocean science rarely does. It was a daring milestone that briefly put downward exploration on the same cultural stage as upward exploration. Yet oddly, it did not trigger an immediate sustained era of frequent crewed returns to Hadal depths. Instead, it became a peak followed by a long lull, which we'll unpack in the next chapters. So think of Trieste as a hinge moment. It closes the age of wondering whether humans could physically reach the deepest seafloor, and it opens the age of asking why, after proving it was possible, we didn't keep doing it at scale. This is one of those moments in exploration history that's small in the logbook and huge in the mythology. After Trieste reached the bottom in 1960, Jacques Piccard and Don Walsh reported seeing what looked like a flatfish-like animal, sometimes described in retellings as a soul, moving on the seafloor. If you're lecturing to an audience, this is a great place to slow down and model good historical thinking, because the question isn't who was right and who was wrong in a courtroom sense. The question is what this claim tells us about human perception, the limits of early deep-sea observation, and how science corrects itself over time without turning pioneers into villains. Let's start with what we can say cleanly. They were two skilled observers in a tiny sphere, looking through a view that was not panoramic, at a seafloor lit by artificial lights after a long descent, under stress, with a vehicle that had already made a worrying cracking sound earlier in the dive. That is not a neutral lab environment. That's an extreme field observation with all the usual challenges multiplied. The deep is visually deceptive. Scale is hard to judge. Movement looks odd in suspended sediment, and your brain tries to map unfamiliar shapes onto the closest familiar category. So, it looked like a fish is psychologically plausible, even if the identity is uncertain. Now the biological side. Modern research has shown that life in the Hadal zone is real and diverse in its own way, especially microbes and invertebrates like amphipods. But when we talk about fish specifically, the strongest evidence we have so far suggests a depth limit for true fish populations well above the absolute bottom of Challenger Deep. The deepest confirmed observations and captures of Hadal snailfish in the Mariana region are around the low 8,000-meter range, not near 10,900 meters. That matters for this story because it implies that a vertebrate fish swimming at the very deepest point would be surprising given what we currently understand about physiology under extreme pressure. This is not just a vibe check. Pressure affects proteins and cell membranes in ways that become harder and harder to manage for complex animals. And while evolution can do astonishing things, there do appear to be practical biochemical limits. So the modern scientific consensus leans toward doubt that Trieste saw a flatfish at the deepest seafloor. That doesn't mean they made it up. It means they likely misidentified something. A large amphipod catching the light at the right angle, a sea cucumber shifting across sediment, or another invertebrate moving in a way that momentarily resembled a fish silhouette could all fit a reasonable reinterpretation. In a history of science frame, this is actually a healthy example of how knowledge is built. The first humans to enter an environment often describe it using the vocabulary they already have. Later generations refine the vocabulary and reclassify what was seen. The key is that early accounts are still valuable because they capture the human encounter with the unknown, even when they don't provide the last word on taxonomy. There's also a deeper cultural punchline here. The fish story stuck because it gave the abyss a familiar face. A fish at the bottom of the world is narratively perfect. It makes the trench feel less abstract. It implies an ecosystem we can instantly picture. In other words, the claim wasn't only biological, it was also symbolic, and symbols travel farther than careful footnotes. So when you present this in your lecture, you can do something that's both fair to the historical actors and faithful to modern science. Say that Piccard and Walsh reported seeing something fish-like, that later evidence makes a vertebrate fish at that exact depth unlikely, and that the mystery remains a useful teaching case in the limits of observation under extreme conditions. If you deliver it that way, you're not tearing down the Trieste achievement. You're showing the audience how science respects the past while still updating the record. And that sets up the emotional logic of the next chapter perfectly. Because after a moment this iconic, you would expect a fast, booming era of deeper and deeper human dives. Instead, we get a long, quiet gap. The question becomes not, what did they see, but why didn't we go back for so long? The title sounds a little dramatic, so let's define what we mean so we don't accidentally teach a myth. After the Trieste dive in 1960, humanity did not completely stop studying the Mariana Trench. What essentially paused was the crude, headline-grabbing, two humans in a sphere at the very bottom kind of exploration. There was a long gap before another person went back to Challenger Deep. That gap lasted until 2012, when James Cameron made his solo dive. So when we say 50 years of silence, we're really talking about the silence of human bodies down there, not the silence of science altogether. And that distinction is important because it helps explain the real reasons for the pause. This wasn't one single decision like, okay, we're done. It was a slow drift of priorities. First, cost and risk. A Hadal-capable crewed vehicle is not just a submarine with an attitude, it's a custom engineering project. The pressure sphere, the seals, the buoyancy design, the testing requirements, the ship's support, the safety protocols, none of that is cheap. And at that extreme depth, you can't pretend failure would be a small incident. So after Trieste proved it was possible, the next question became, is repeating this worth the expense and danger compared with other kinds of ocean science we could do for the same money? For a while, many institutions quietly answered, not really. Second, the space age sucked a lot of oxygen out of the room. The 1960s were the peak years of national prestige tied to upward exploration. If you're a government trying to make a symbolic point about technology and power, the moon beats the trench in terms of public attention. That's not a scientific argument. That's a cultural reality. Budgets follow narratives, and the narrative of the era had a launch pad, not a winch cable. Third, the Cold War pushed ocean technology in a different direction. The military value of the ocean was enormous, but that value didn't always align with sending humans to the deepest seafloor. Anti-submarine warfare, undersea surveillance, mapping for navigation, and better understanding of sound propagation in the water column were all intensely important. You could argue that some deep ocean research benefited from military interest, and that's true, but the specific niche of crude Hadal descent wasn't automatically a top priority. The deep ocean was strategically relevant as a medium and a battleground of sensors more than as a destination for people. Fourth, the rise of uncrewed systems changed the logic of exploration. By the late 20th century, remotely operated vehicles and deep-sea landers became more capable and, in many cases, more scientifically efficient. If your goal is to collect samples, measure chemistry, map terrain, or deploy instruments for long-term data, you don't strictly need a human at the bottom. You need reliable hardware. And that reality got clearer as technology improved. The Japanese ROV Kaiko, for example, reached the Challenger Deep area in the 1990s and returned samples, which was a huge scientific step, even without a crewed sphere. So, in a quiet way, the uncrewed route was proving that you could keep learning without taking the full human risk leap every time. Fifth, there's an uncomfortable truth about scientific payoff versus spectacle. The first crewed visit to the deepest point is a historic milestone. The second, third, and fourth crewed visits need a clearer research justification to compete with other priorities. In other words, the Trieste dive was a proof of possibility moment. After that, the bar for repeating the feat was higher. That's normal in science. A breakthrough demo is one thing, routine access is another. And routine access to Hadal depths is still difficult even today. So the 50-year gap becomes less mysterious if you frame it this way. The world didn't lose curiosity. It temporarily lost a good cost-to-benefit argument for humans going all the way down. The deep ocean was still being mapped and sampled. The trench was still in the scientific literature, but the human presence angle went quiet. Now, to make this chapter work as history, and not just engineering economics, you can also emphasize the psychology of risk. After a pioneering moment, institutions often step back and reassess. Some of that is rational caution. Some of it is bureaucracy. Some of it is the fact that such missions need champions, specific people who fight for funding and attention year after year. If those champions retire or priorities shift, a field can stall even if the underlying curiosity remains. That's not unique to oceanography. It's a general pattern in big science. And it sets us up for the return of high-profile dives in the 2000s and 2010s, when new private funding, new materials, improved navigation tools, and better imaging made the case for going back in person seem exciting and achievable again. So if you want a clean closing line for your spoken delivery, keep it grounded. We didn't abandon the Mariana Trench because it stopped mattering. We paused crewed trips because the trench is expensive, unforgiving, and scientifically reachable in other ways. The silence was not emptiness. It was a shift in method and in what the world was willing to pay for at that moment in history. After the Trieste chapter and that long pause we just talked about, the return of a human to Challenger Deep in 2012 feels like history snapping back into motion. And it didn't come from a national navy this time. It came from a filmmaker with an engineer's obsession and a very modern style of ambition. On March 26, 2012, James Cameron piloted the Deep-Sea Challenger to the bottom of Challenger Deep, reaching roughly 10.9 kilometers down. The exact depth figured depends on instrument and method, but the core milestone is stable and uncontested. He became the first person to make a solo descent to the deepest known point in the ocean and the third human being to reach it overall after Piccard and Walsh in 1960. The cultural contrast is part of why this matters. Trieste sits inside a Cold War framework of naval capability and state-scale engineering. Cameron's dive sits inside a 21st century framework where private funding, media storytelling, and high-end custom tech can restart something that governments had largely set aside. That shift is not just a footnote, it's a sign of how exploration economics changed. In this era, an individual with resources, a strong narrative, and the right technical partnerships can build a machine that competes with state projects, at least for a specific mission. The deep-sea Challenger itself was a different kind of design than Trieste. Instead of a big float with a small crew sphere hanging beneath, Cameron's sub was a tall, slim, vertically oriented vehicle with a single-person pressure sphere near the base. The shape was partly about efficiency and controllability, and partly about what new materials and systems could support. It was built to carry cameras, lights, sampling tools, and scientific instruments alongside the human pilot. This wasn't only a stunt, it was meant to create data and samples, and to show that modern technology could make Hadal science more repeatable. The dive profile is worth giving your audience in human terms. The descent took hours. The bottom phase lasted on the order of a few hours, and camera reported a seafloor that looked like a pale, fine sediment plain in the area he reached, with limited large visible life in the immediate field of view. He collected samples of sediment and rock and water, and he attempted extensive imaging. But the deep ocean doesn't care who you are, and it doesn't respect the fact that your mission is historic. The dive encountered technical issues, including system problems, that reduced how much he could travel laterally on the bottom. That detail is useful in a lecture because it keeps the story honest. Even with modern engineering, the Hadal zone is still a place where the margin for error is thin and the environment can dictate the rules minute by minute. Historically, the Cameron dive did two things at once. It reopened public imagination. Suddenly, the Mariana Trench was back in mainstream conversation, not just in the specialized literature. And it also helped normalize the idea that advanced, privately backed deep ocean projects could contribute meaningfully to science, especially when they coordinate with research institutions for sample analysis and data sharing. If Trieste was the proof that humans could get there, and then we drifted into decades of uncrewed emphasis, Cameron's dive became a symbolic bridge into a new mixed model: humans, robots, and high-precision mapping, all supporting the same broad goal of understanding the Hadal world. So the way I'd land this chapter in a spoken lecture is pretty simple. 2012 wasn't just a celebrity visiting a record holder. It was the moment the trench moved from a half-century-old legend back into active, modern exploration, with new tools, new funding logic, and a renewed argument that the deepest seafloor is not a historical trophy, but a scientific frontier that can still surprise us. Challenger Deep is one of those names that sounds like it was invented for a movie, but the reality behind it is more precise and honestly more interesting. This is the deepest known point in Earth's ocean, located within the southern part of the Mariana Trench. When people say the Mariana Trench, they often imagine one single pit, but Challenger Deep is better understood as a specific deep area with multiple basins and complex topography, shaped by subduction and faulting. In other words, Not a tidy drain in the seafloor, but a rugged, active geological low point, part of a system that is still evolving. The best modern depth estimates cluster around about 10.9 kilometers. You will hear slightly different numbers depending on the expedition and the instruments used, but you can safely tell your audience that the deepest seafloor currently measured in this area is roughly 10,900 to 10,935 meters. That range is a simple way to stay accurate without pretending the ocean floor is a single mathematically perfect number. Even saying that out loud helps people realize how measurement itself is part of this story. The sea is not easy to pin down. So what does it mean to call this a journey to the bottom of gravity? I'd interpret that phrase in a grounded way for a lecture. It's not that gravity is stronger there in any meaningful, everyday sense. It's that this is where the weight of the ocean becomes as close to absolute as humans can encounter on Earth. The pressure at these depths is around 1,100 atmospheres. The water column is the story. That is the real barrier. The real reason this depth is historically rare for crewed visits. So the journey is partly physical and partly technological. You're not just traveling downward, you're traveling into a regime where the environment enforces a new set of rules on material science and human decision-making. If you want to make this chapter feel vivid without slipping into mythology, it helps to walk the audience through the layered experience of reaching the bottom. The descent is long, often several hours. You pass through zones that are familiar to oceanographers, but not to the general public. The sunlit epipelagic, the dim mesopelagic, the midnight bathypelagic, then the abyssal plain depths that already feel unreachable to most people, and finally the Hadal zone, which is largely confined to deep trenches. The biological and chemical context changes as you go. The light disappears entirely. The temperature drops. The food supply becomes more sporadic, and yet the deep is not empty. It is a place of extreme selection, not a lifeless void. Sediments accumulate. Organic matter drifts down in a slow snow, sometimes interrupted by sudden windfalls like large carcasses. Microbial processes continue. Invertebrates thrive in specialized forms. Fish appear in the broader Hadal neighborhood, though evidence suggests a practical depth ceiling for fish well above the very deepest seafloor. What humans experience at the bottom historically has been shaped by the vehicles we send. The Trieste in 1960 was a blunt triumph. It proved that a crewed descent to the deepest seafloor was possible, even with mid-century technology and a design that looks almost improvised by modern standards. The reported cracking of a window component during that dive has become part of the lore, but the deeper lesson is the engineering mindset of the era. Accept risk, trust the core sphere, and proceed. Then the long gap followed, not because scientists stopped caring, but because the cost, risk, and limited immediate payoff made frequent crewed repeats hard to justify, when uncrewed systems could gather valuable data. That context matters because it reframes Cameron's 2012 dive. His solo descent was not just a personal feat. It was a signal that the economics and technology of Hadal access had matured enough for a new model of exploration, where private capital and modern materials could complement institutional science. If you're looking for the historical through line for this chapter, it's this. Challenger Deep is a place where human exploration has moved in pulses. First, the era of surface measurement. Then the dramatic proof of possibility with Trieste, then decades of quieter, instrument-led science, then a return of high-profile crewed visits as technology and funding pathways diversified. This pulse pattern is common in the history of extreme environments. The environment doesn't change, our capacity and our priorities do. Now, in the context of your lecture, this chapter can also serve as a conceptual summary of what deepest place really means scientifically. It's not a trophy label. It's a node where multiple disciplines converge. Geology explains the trench's existence through subduction and plate dynamics. Physics explains the pressure regime that governs everything from hull design to protein stability. Biology explores how life adapts at the outer edge of what complex organisms can tolerate. And human history ties these threads to war, national prestige, private ambition, and the slow evolution of scientific instrumentation. You can even bring the audience back to a simple, almost humble point. The deepest seafloor is not just a location we visit, it's a place we learn to measure, interpret, and protect. Because once we can reach a place consistently, we can also impact it consistently. That opens ethical and policy questions that will matter more in Part 4 when we discuss pollution and mining. So the best way to end this chapter, in a calm lecture voice, is to treat Challenger Deep as a symbol with real material stakes. It is a geographical extreme, yes, but it is also a test of how civilization engages with environments that don't forgive shortcuts. When we talk about reaching the bottom of the ocean, we're really talking about the limits of our tools, the patience of our institutions, and the quality of our scientific curiosity. And that takes us cleanly into Part 3, where the main character shifts again, from machines and milestones to life itself in the shadow biosphere. Up to now, we've been talking about depth as a human problem, pressure, engineering, the history of who went down and when. Now we pivot to the part that usually surprises people the most. The deep ocean is not only a hostile place, it's a living place, and not in a vague, maybe there are germs way, but in a structured, evolving, scientifically documented way. The key concept for this chapter is simple and powerful. Life does not require sunlight in every setting. On the surface, our everyday intuition says energy equals the sun, photosynthesis equals food webs. That's mostly true for the world we see, but it's not the whole story of Earth. In the deep sea, especially far below the photic zone, ecosystems can be powered by chemical energy. That process is chemosynthesis. Instead of using light to convert carbon dioxide into organic matter, chemosynthetic organisms use energy released by chemical reactions, often involving hydrogen sulfide, methane, hydrogen, or other reduced compounds coming from Earth's interior or from reactions between seawater and rock. The big historical turning point here is the discovery of hydrothermal vent ecosystems in 1977 near the Galapagos Rift. Scientists found dense communities of organisms thriving around superheated, mineral-rich fluids venting from the sea floor. This was not a minor tweak to biology. It was a rewrite of assumptions. The deep sea was no longer only a graveyard fed by leftovers drifting down from above. It also had places where Earth's internal chemistry could directly fuel local oases of life. These ecosystems rely on microbes that form the base of the food chain, and then larger animals like tube worms, clams, mussels, and shrimp in many vent systems depend on them directly or indirectly. So you get something that feels almost upside down compared with the surface. Instead of plants using sunlight and animals eating plants, you have bacteria using chemistry and animals building their lives around bacterial production. Now, how does this connect to the Mariana Trench specifically? This is where we need to be careful and precise. The deepest floor of Challenger Deep is not a classic hydrothermal vent field in the way people imagine black smokers on a mid-ocean ridge. The Mariana system is a subduction zone, not a spreading ridge, and the trench environment is dominated by extreme depth, cold temperatures, and sediments that can accumulate organic material from the surface ocean. That means a lot of Hadal trench life is still supported by a detrital food web, marine snow, carcass falls, and material that slides or settles into the trench over time. In that sense, the trench is often more like a deep collector than a chemical factory. But the broader Mariana region absolutely connects to chemosynthetic ecology because subduction zones and volcanic arcs can host hydrothermal activity, and forearc settings in the Marianas are known for unusual geochemical systems where fluids and altered rocks create distinctive habitats for microbes. In a lecture, you can say this without getting lost in the weeds. The Mariana Trench sits within a tectonically and chemically active neighborhood, and even if the very deepest basin is not a classic hydrothermal scene, the same earth processes that carve the trench also drive the chemistry that makes deep chemosynthetic life possible in nearby settings. That lets you keep the narrative honest. Another point that's worth saying out loud to an American audience is that chemosynthesis reshaped how scientists think about the boundaries of habitability. If life can run on chemical gradients in darkness at high pressure, then the deep ocean becomes more than an Earth curiosity. It becomes an analog for places beyond Earth where sunlight is weak or absent. That's a bridge to your later chapter on Europa and Enceladus, but we don't need to jump there yet. We just need to plant the idea that the deep sea helped expand the definition of where life might exist. So what does life actually have to do to survive without sunlight? Two big strategies. One is to live near chemical sources, vents, seeps, or geologically active zones, and build ecology around them. The second is to become extremely efficient at using scarce organic matter drifting down from the surface. The Mariana Trench likely supports both strategies across its broader system. Microbes in sediments can process organic carbon under high pressure. Scavengers and detrivores can exploit food that accumulates preferentially in trench topography. The trench shape matters here. It can funnel and trap material from above or from the trench walls, which means in some ways the Hadal environment can be richer than you'd expect purely from depth alone. That doesn't mean it's lush in a shallow water sense. It means life is opportunistic and adapted to pulse events and long, lean stretches. This is the kind of nuance that makes your lecture sound human and credible. The deep ocean is not uniformly starving and not uniformly abundant. It's a system of scarcity with occasional jackpots, and these jackpots can shape evolution. One more detail that helps lock in the concept. Chemosynthesis is not a weird exception anymore. It is a recognized fundamental mode of primary production on Earth, even if it is geographically limited compared with photosynthesis. The deep ocean's energy map is patchy, but patchy doesn't mean unimportant. It means that if you place yourself in the mindset of a deep-sea organism, finding a chemical energy source is like finding a city in a desert. The city might be small relative to the planet, but for the organisms that live there, it's everything.
So where does this leave us as historians telling a story? It gives us a clean narrative shift. The Mariana Trench is not only a record holder for depth, it's part of the broader revolution in late 20th century ocean science that proved darkness is not equal to lifelessness. The deep sea forced humans to update their mental model of life's dependence on the sun. We didn't abandon the solar model, we expanded it. The ocean taught us that Earth has two great energy economies running in parallel: the bright, vast surface economy powered by light, and the small but scientifically profound deep economy powered by chemistry and geology. That's the foundation for the rest of Part 3, where we'll get more specific about vents, unusual chemical oases, and the astonishing animals that treat extreme pressure as a normal Tuesday.
Let's get concrete about the weird chemistry cities of the deep, because chemosynthesis stays abstract until you picture the plumbing. Hydrothermal vents form where seawater seeps into cracks in the ocean crust, gets heated by magma or hot rock, reacts with minerals, and then blasts back out loaded with dissolved chemicals and metals. When that superheated fluid hits cold seawater, minerals precipitate fast, building chimney-like structures over time. The iconic version is the black smoker, usually found along mid-ocean ridges and also in some back arc settings. These vents can reach temperatures around 350 to 400 degrees Celsius, and the black look comes from clouds of metal sulfide particles that form as the vent fluid mixes with seawater. Around them, microbes use chemical energy, often from hydrogen sulfide, hydrogen, or methane, to fix carbon, and that microbial production becomes the base of a compact, high-biomass food web. This is the classic oasis in a desert pattern of the deep ocean, but without the romance. A small patch of extreme chemistry can support dense communities of larger animals that would have no reason to exist in the surrounding plain. Now, if your audience is thinking, okay, so this is mostly a ridge story, what does it have to do with the Marianas? Good question. The Mariana Trench proper is a subduction trench, not a ridge. So the very deepest basins are not where you expect the textbook black smoker fields. But the broader Mariana region includes a volcanic arc and a back arc basin, and those environments absolutely host hydrothermal systems, including high-temperature ones. Subduction zones add an extra layer of chemistry to the mix, because water and other volatiles carried down by the subducting plate change melting behavior and fluid composition. So the Marianas are one of those places where you can compare vent styles within the same large tectonic neighborhood. And then there's the famous twist that makes the phrase champagne vents more than a cute label. Near the Mariana Arc, at a submarine volcano called NW Ifuku, researchers identified a vent site that emits bubbles of liquid carbon dioxide. Yes, actual CO2 in liquid form under deep sea pressure, rising like a stream of fizz, which is why people nicknamed it the champagne vent. This isn't a Challenger deep phenomenon. It's a reminder that the Mariana system is chemically diverse across depths and settings, and that deep-sea vents are not one uniform category. For your lecture, the takeaway is crisp. Black smokers represent the high-temperature, metal-rich end of hydrothermal life support systems, while unusual CO2-rich vents show how subduction-related volcanism can create chemically distinctive habitats.
Both expand the story of how life taps Earth's internal energy, and both help us avoid a simplistic idea that the deep sea is fed only by leftovers from the surface. These sites are small on a map, but they are big in meaning, because they prove that geology can act like an engine for biology. And that leads us nicely into the next chapter, where we'll narrow the lens even more and talk about how life adapts to the crushing pressure itself, with the Mariana snailfish as the headline example of what evolution can do right up against the edge of the possible.
Let's put a real animal at the center of this pressure story, because otherwise Hadal life can sound like a cloud of abstract microbes. The Mariana snailfish is the headline example for a reason. It's a small, pale, gelatinous-looking fish from the Hadal zone of the Mariana Trench, and it became famous because it represents, as far as we currently know, the deepest living fish group that science has documented with solid evidence. When people say a fish that melts, I want you to hear that as a dramatic shortcut, not a literal description. What's true is that these fish are exquisitely tuned to extreme pressure and cold, and when you rapidly bring them to the surface, their bodies don't handle the change well at all. The tissues are soft, the structural support is minimal, and without the pressure they're built for, they can be badly damaged. So yes, they can look like they fall apart in a way that feels almost unreal to anyone used to normal fish anatomy, but the biology behind it is rigorous and explainable. The basic challenge is this: at around 7,000 to 8,000 meters deep, pressure is hundreds of atmospheres higher than what most vertebrates can tolerate. The Mariana snailfish lineage seems to meet that challenge using a suite of adaptations that are subtle individually but powerful together. They don't have large gas-filled spaces like a swim bladder, which would be a liability under intense pressure. Their skeletons tend to be lightly ossified, reducing rigid structures that aren't necessary in a world where buoyancy and locomotion work differently. Their bodies are often described as gelatinous because they rely on soft tissue and a water-rich structure that functions perfectly fine under pressure. They also use biochemical tricks. Organisms at great depth commonly rely on molecules called osmolytes to stabilize proteins under pressure. One of the best known is TMAO, which helps keep cellular proteins functioning when the surrounding physical forces would otherwise distort them. The catch is that this strategy likely has limits, which is one reason many researchers think there's a practical depth ceiling for fish well above the absolute deepest seafloor of Challenger Deep. The Mariana snailfish sits right near that boundary zone, living proof that evolution can push vertebrate life extremely far, but also hinting that there may be a hard edge to how far fish-style physiology can go. This is a great moment to remind your audience of something important. The trench is not uniformly the same environment. The Hadal zone is shaped by steep walls, ridges, basins, and sediment plains, and animals exploit these microhabitats. Snailfish are not necessarily hanging out at the single deepest number on a map. They appear in the broader Hadal depths, where the ecosystem structure, prey availability, and chemistry support a stable life strategy. And they're not monsters or freaks of nature. In their own world, they're just fish doing fish things, eating small crustaceans, moving through the water with a kind of calm efficiency that looks almost slow motion to us, because we keep imagining deep life as either frantic or non-existent. The deeper lesson here is a historical one as much as a biological one.
The Mariana Snailfish era shows how modern deep-sea science shifted away from pure "can we reach it" toward what lives there and how does it work. Improved cameras, landers, baited traps, and genetic tools let scientists document Hadal vertebrates without needing a human in a capsule every time. So this fish becomes a symbol of the newer phase of exploration, less about one heroic descent, more about repeated, careful evidence building. If you want a clean closing note for your lecture voice, try this idea. The Mariana snailfish doesn't just survive pressure, it institutionalizes it. Its body chemistry and architecture assume the crush as normal. And that's the kind of adaptation that turns the Mariana Trench from a scary geology headline into a real living habitat with its own rules of its own. If the Mariana snailfish shows us how vertebrates negotiate the edge of survivable pressure, giant amphipods show us something different and maybe even weirder in its own way. The deep sea can stretch the body plan of some animals into sizes that feel almost out of place. This is the phenomenon we call deep-sea gigantism, and the basic idea is simple. In certain deep environments, some species grow much larger than their close relatives in shallow water. It's not universal, it's not a rule that everything gets bigger in the deep, but when it happens, it's striking. Amphipods are a great example because most people who have never studied marine biology already have a mental image of an amphipod as a small, shrimp-like creature you might barely notice. In shallow water, many amphipods are just a centimeter or two long, maybe a bit more. Now, jump to the Hadal world and suddenly you're hearing about amphipods that can reach lengths over 30 centimeters, sometimes called supergiant amphipods. In the Mariana region, the species most often associated with this headline is Alicella gigantea, one of the largest known amphipods, recorded from great depths in the Pacific and other deep settings. The exact maximum size varies by report and specimen condition, but the key fact is stable. This is not a slightly bigger cousin. This is an animal whose scale changes how we think about what a normal amphipod can be. So why might gigantism happen at all? The honest answer is that we have good hypotheses and partial evidence, but not a single universal explanation that fits every group. In science, this is one of those multiple causes, different lineages problems. But for amphipods and other deep-sea giants, a few ideas keep coming back because they make ecological and physiological sense. One is temperature. Cold environments generally slow metabolism. If you're a deep-sea animal with a slower life pace, you may live longer and delay reproduction, which can allow larger body size to evolve. That's a broad ecological pattern seen in various cold water systems, not only the trenches. Another is food strategy. The trench is a landscape that can trap and concentrate organic material from above, and it also receives occasional huge jackpots, dead fish, large carcasses, even whale falls in broader abyssal settings. A bigger scavenger may have an advantage here. Size lets you store energy, travel farther across the seafloor, and compete at a food fall. If you've ever watched time-lapse footage of baited deep-sea landers, you see how quickly amphipods can arrive and how densely they can swarm. A large body is not just a flex, it's a tool for surviving a feast and famine economy. Another idea has to do with oxygen and circulation. In some deep environments, oxygen availability and stable cold conditions may favor certain respiratory efficiencies, but this one gets complicated because oxygen patterns vary regionally and with depth. The trenches are not uniform chemistry tubes. So you can mention oxygen as part of the conversation without overselling it as the answer. Pressure itself could also play a role indirectly by shaping predator-prey systems and limiting which groups can occupy certain niches. If the roster of predators and competitors changes with depth, evolution can push body size in unexpected directions. But again, we should keep the story careful. Pressure doesn't automatically make things bigger, it just changes the playing field. It's also worth saying out loud that deep-sea gigantism sits next to its cousin concept, deep-sea dwarfism. In some groups, the deep favors smaller sizes instead. Evolution is not making a single aesthetic choice, it's responding to local trade-offs. The deep is a mosaic of selection pressures, not a single monotone environment. Amphipods just happen to be one of the groups where the gigantism pattern is dramatic enough to capture attention. Now, why should a history of science lecture care about amphipod size? Because this is where technology really shapes discovery. We didn't know about these giants in a reliable way until we had more consistent deep-sea sampling methods, baited traps, landers, high-quality imaging, and the ability to recover specimens without destroying them in the process. The trench doesn't give up evidence easily. Soft-bodied and pressure-adapted organisms can be damaged during ascent. So part of what we're really discussing here is the history of observation. Giant amphipods became a public-facing symbol of trench life because modern tools let us document them in ways that earlier generations simply couldn't. And once you see a big amphipod next to a standard bait housing or instrument frame, your brain flips a switch. It becomes clear that the Hadal zone is not a sterile bottom-of-the-map footnote. It's a habitat with its own ecology, its own energy rules, and its own creatures that are not small by default. One last nuance that usually lands well with a US audience. Gigantism is also a reminder that we shouldn't define extreme only by numbers like depth and pressure. The extreme can be biological design, too. The trench doesn't just test materials, it tests our assumptions about what life should look like. When a group we think of as tiny becomes huge, it's a quiet lesson in humility. The Mariana Trench is full of those lessons. So this chapter leaves us with a simple, grounded conclusion. Deep-sea gigantism in amphipods is likely an adaptive response to cold, scarcity punctuated by sudden abundance, and a distinct Hadal competitive landscape. It doesn't mean every trench animal grows large. It means evolution is opportunistic. And in some cases, a bigger body is the winning solution. And that brings us smoothly to the next chapter, because size is only one way to survive the deep, and another is to manipulate light, make it, hide it, weaponize it, which is where bioluminescence becomes the next piece of the story.
If the last chapter was about size and brute survival, this one is about something that feels almost unfairly clever: light. In the deep sea, in a place where sunlight is gone. So where does the light come from? Living things make it. Bioluminescence is the production of light by organisms through chemical reactions, usually involving a light-emitting molecule, luciferin, and an enzyme, luciferase, though the exact chemistry varies across groups. That's the simple version you can say out loud without turning the lecture into biochemistry class. The deeper truth is that bioluminescence has evolved many times independently in the ocean. It's not one big family trick shared by all deep animals. It's a bunch of separate evolutionary inventions
that landed on the same solution because the deep ocean rewards that solution. Now, here's a detail that helps anchor this for a general U.S. audience. Bioluminescence is extremely common in the open ocean's mid-water depths. The darker it gets, the more useful light becomes as an information tool. So the classic bioluminescent zone is not necessarily the very bottom of a trench. It's the broad, deep water column where animals encounter each other in near total darkness, where a small flash can be the difference between eating, escaping, or finding a mate. In the Hadal Trench environment, especially right down near the deepest basins, we probably should be more cautious in how we phrase abundance. The biology there is harder to observe and sample, and many trench communities are dominated by scavengers and sediment dwellers. So the safe, honest way to say it is this: bioluminescence is a major feature of deep ocean life overall, and it likely plays roles in parts of the Mariana system. But the most famous bioluminescent strategies we talk about are best documented in the wider deep sea, rather than only at the absolute deepest trench floor. Okay, so what does bioluminescence do? The title gives us 3 functions, and each one maps to a genuine scientific idea. First, weapon. Not a laser beam, obviously. More like a tactical flash. Some animals use bursts of light as a startle response, which can confuse predators for a split second. Others may use what marine biologists sometimes call a burglar alarm strategy. If you're being attacked, you produce light to attract a bigger predator that might attack your attacker. It's chaotic, but it can work. There are also deep-sea organisms that release glowing secretions, sometimes compared to a kind of luminous smoke screen. The predator gets a bright distraction, and the prey gets a chance to disappear into the dark. Second, lure. This is what most non-specialists already know because the anglerfish is basically the mascot of deep-sea creepiness. The classic image is a fish with a bioluminescent lure dangling in front of its mouth. And yes, that's real. In some anglerfish species, the light is produced by symbiotic bacteria living in a specialized organ. The logic is brutally efficient. In darkness, curiosity is deadly. A little moving light can be mistaken for prey or harmless drifting life. Then the mouth opens, and that's the end of the story. This is a great example for your lecture because it shows the deep sea doesn't only select for toughness, it selects for strategy. Third, invisibility cloak. This is where the wording sounds sci-fi, but the underlying mechanism is straightforward. Counter-illumination is a method used chiefly by midwater animals. In regions where there is still faint downwelling light from above, an animal's silhouette can be visible to predators looking upward. So some creatures produce light on their undersides to match the brightness and color of the light coming from above, effectively erasing their shadow. It's camouflage by imitation. The trick is that this works best in the water column, where there is still some ambient light to match. At extreme Hadal depths, near 10,000 meters, you wouldn't expect counter-illumination to be the dominant survival tool because there's no natural light left to blend into. So in your delivery, you can keep this honest by saying counter-illumination is a key deep ocean strategy broadly, even if it's more relevant to the midwater constituency of the deep than to the very deepest trench floor. Now, let's connect this to the larger theme of adaptation, under pressure, literally and figuratively. Producing light costs energy. That's important. If there's one point I'd emphasize to avoid romanticizing bioluminescence, it's that evolution doesn't hand out expensive tricks unless they pay rent. In the deep sea, where food can be scarce, a bioluminescent system that wastes energy would be weeded out. So the persistence of bioluminescence tells us it confers real advantages. The deep is economical in a harsh way. If a trait survives there, it's usually because it's earning its keep. Bioluminescence also intersects with communication. In some groups, light patterns likely help with species recognition or mating. Imagine a world with no daylight, no color cues, limited scent dispersal, and huge empty spaces. A specific blimp pattern could function like a handshake, a name tag, and an invitation all at once. We don't have full decoding for most of these systems, and we shouldn't pretend we do, but the theory is consistent with what we know about how animals signal in low-visibility environments. There's a small historical layer here too, which quietly helps your lecture sound richer. Bioluminescence wasn't discovered in the deep sea in one cinematic moment. People observed glowing organisms near the surface for centuries, but the understanding that bioluminescence is a large-scale, structurally important feature of deep ocean ecosystems matured with better deep-sea imaging and more reliable specimen collection. In other words, this is another case where technology didn't just confirm a cool fact, it changed the shape of what we thought the deep sea was. The ocean became not just dark, but actively lit in ways we couldn't have guessed by staying near shore. So if you want a calm, memorable landing for this chapter, try this idea. In the deep ocean, light is language and misdirection at the same time. It can feed you, hide you, warn you, or betray the thing trying to eat you. The Mariana Trench sits in a broader deep-sea world where bioluminescence is one of evolution's most effective tools for dealing with darkness. It's not magic, it's chemistry with survival logic. And this closes part 3 nicely. We've gone from energy without sunlight to chemical oases, to pressure-adapted fish, to oversized scavengers, and now to the deep's private light economy. The next step is to bring humans back into the frame in a direct way, because once you accept that this is a living, structured system, you also have to face the uncomfortable question, what happens when our waste, our technology, and our economic ambitions sink into it?
If part 3 was the deep ocean as a living system, part 4 is where we add the awkward human question hovering in the background. What kind of system are we impacting without really seeing it? But before we get to plastic, mining, and Cold War hardware, we need to talk about the deep sea's basic food economy, because everything else sits on top of that. And the economy down there is weirdly conservative, almost miserly, punctuated by these sudden, dramatic windfalls. 2 ideas anchor this chapter: marine snow and whale falls. Marine snow is the steady drip of nutrition from the surface ocean to the deep. It's not literal snow, obviously, but the metaphor is useful if you keep it light. We're talking about tiny particles of dead plankton, fecal pellets, discarded mucus, bits of organic debris, all clumping together and sinking. It's the main reason the abyss isn't completely starved. But the key detail is that by the time this material reaches great depths, much of the energy has already been eaten, decomposed, or recycled higher up. So what arrives is thinner, more sporadic, and less rich than what started the journey.
That means deep ecosystems often live in a long, low-calorie reality, and they're built for patience. Now here's where trenches like the Mariana can behave a little differently from the flat abyssal plains nearby. A trench is a topographic collector. It can funnel and trap organic matter that slides down slopes or settles into basins. So while the Hadal zone is extreme in pressure and darkness, it can sometimes be relatively enriched in the right places compared with what you'd predict if you only did the deeper equals less food equation. It's not a buffet. It's more like a pantry that gets refilled unevenly, with some shelves mysteriously fuller than expected because gravity and seafloor shape are doing their quiet work. Now put that slow trickle next to the opposite extreme, whale falls. When a whale dies and sinks, it delivers a huge, concentrated package of carbon and nutrients to the deep seafloor. This is one of the most dramatic food jackpot events in the ocean. A large whale can represent tens of tons of organic material arriving in one place all at once. And the ecological ripple is not small. It can build a temporary community that moves through fairly recognizable stages. First comes a mobile scavenger stage, where sharks, hagfish, amphipods, and other scavengers strip soft tissue. This can last months to maybe a couple of years, depending on depth, oxygen, and the local scavenger community. Then you get what's often described as an enrichment opportunist stage, where smaller organisms colonize the enriched sediments around the carcass. After that, in many cases, there is a sulfophilic stage, where bacteria break down lipids in the bones and produce sulfide, supporting chemosynthetic communities that can include specialized worms and mollusks. In some documented cases, this stage can persist for years and even decades. Eventually, what remains can act like a reef-like hard substrate, giving the deep sea a rare kind of physical structure in an environment that is otherwise mostly soft sediment. So the whale fall is not just a meal, it's a temporary habitat, a chemical reactor, and a biodiversity event. For the Mariana context, we should be precise with phrasing. Whale falls are best documented across abyssal depths, and while it is plausible that whale carcasses can reach very deep trench environments, the frequency and community details in the deepest Hadal basins are harder to document and likely rarer. But the larger Mariana system almost certainly experiences this feast and famine pattern in different ways across depth zones. Even if the absolute deepest floor doesn't regularly host classic whalefall communities, the concept is still essential for understanding how big pulses of organic matter shape deep-sea evolution and survival strategies. It also connects to why giant amphipods make ecological sense. If your world is mostly scarcity with rare, massive paydays, being built to capitalize quickly on a sudden food source is a smart evolutionary bet. The history of science angle here is subtle but useful. The whale fall concept became a serious ecological framework only after deep-sea observation improved. Before reliable submersibles, ROVs, and baited landers, the deep was easy to imagine as uniform emptiness. Whale falls shattered that idea. They revealed that the deep is not just a continuous gradient of less and less life. It's punctuated by events that create local booms. So the deep sea is not only a place with low energy, it is a place where energy arrives in pulses. That changes how we think about adaptation, population dynamics, and even how resilient these systems might be when humans start adding stressors. And this is the bridge to the rest of Part 4. If the deep sea depends on a fragile balance between slow background supply and rare high-value events, then it becomes especially vulnerable to disruptions that reduce surface productivity, change carbon flux, or contaminate the food that does reach the bottom. It also becomes vulnerable to physical disturbance of the seafloor, because many deep communities may be living on the edge of an energy budget that can't easily absorb shocks. So, the quiet lesson of this chapter is that the Mariana Trench isn't just extreme because it's deep. It's extreme because it sits at the far end of Earth's food conveyor belt. Life there is shaped by endurance, timing, and the ability to seize opportunity when it finally arrives. That's a grounded, non-poetic truth that makes everything else we're about to discuss, military artifacts, plastic, nuclear legacies, and mining, feel more real and more consequential. The Cold War ocean is a strange chapter in modern history, because it's a story where the most important actions often left no visible trace for the public. We think of the Cold War in terms of missiles and ideology and spy planes, but under the surface there was another contest. Who could hear first, hide better, and map the deep with more precision than the other side? And this is where the Mariana region quietly enters the broader narrative, not always as the headline location of a single famous operation, but as part of a strategically important Western Pacific environment near Guam and the Mariana Islands, where U.S. naval presence and undersea awareness mattered a lot. The central technology concept you want your audience to carry is that underwater sound was a kind of superpower. Water carries low-frequency sound incredibly well, and the ocean's layered temperature-pressure structure creates pathways that let those sounds travel far. This is the physics backbone for the Sound Surveillance System, SOSUS, a network of seafloor hydrophones developed by the U.S. beginning in the early Cold War to detect Soviet submarines. The system relied on long-range acoustic monitoring, tied to the reality that submarines, especially earlier generations, produced identifiable low-frequency noise. The public didn't really hear about the system in clear terms until decades later, but within military and intelligence circles, it was part of the strategic nervous system of the ocean. So when you're standing in front of an audience, you can say this plainly. The deep ocean wasn't just a place of science, it was a place of listening, and listening was power. Now, how does a trench fit into this? In two ways that aren't mutually exclusive. First, as an environment that invites instrumentation. Even if specific deployments are not always documented in open sources by location and detail, the logic of the era is clear. Deep-sea basins, slopes, and island arcs offered natural space for testing endurance tech, pressure-resistant housings, cables, sensors, and long-term ocean monitoring strategies. The Mariana area was and remains an important U.S. military region, so it's not a stretch to say that the broader Western Pacific deep-sea environment played a role in the evolution of undersea capability. Second, as a place where things are lost. This is less glamorous but very real. The ocean floor has always been a museum of accidents, failed prototypes, dropped equipment, broken cables, and the quiet debris of decades of experimentation. When you operate in a high-pressure environment where recovery is hard and budgets are finite, some objects simply stay where they fall. The abyss becomes a kind of archive, not because anyone curated it, but because gravity and logistics did. So the phrase "graveyard for failed experiments" should be heard in that practical sense. It's a reminder that technological ambition leaves residue. Even when the mission succeeds, the ocean often keeps the leftovers. If you want to add a human-scale perspective here, you can frame this chapter as a shift in what counts as exploration. During the Cold War, some of the most advanced ocean work was not about visiting the bottom with people. It was about building an invisible infrastructure of detection and mapping. That infrastructure pushed oceanography forward in certain ways. Better understanding of sound propagation, improved seafloor mapping, more robust deepwater materials, and long-term monitoring techniques all benefited from the era's intensity. But it also narrowed the public story. The deep sea became militarily valuable without becoming culturally familiar. That's why when high-profile civilian dives returned later, they felt like a rediscovery to the general public, even though the ocean had never stopped being technologically and strategically active. And this is a good moment to gently complicate the ethics without going full sermon. Undersea surveillance is not automatically evil or automatically heroic. It is a tool built for a specific geopolitical moment. But once you place permanent or semi-permanent systems on the seabed, once you lay cables, drop instruments, abandon damaged units, you start creating an early version of a human footprint in regions that were previously shaped mostly by geology and biology. The trench doesn't care whether the object on the seafloor was scientific, military, or both. It becomes part of the environment either way. So the clean closing idea for this chapter is this. The Mariana Trench sits inside a historical era when the deep ocean became a strategic domain, and the Cold War quietly accelerated the technology needed to sense and survive the abyss. The secrets are not only spy stories, they are also the less cinematic truth that the deep sea began to collect our hardware, our ambitions, and our mistakes long before plastic and mining became the main public concerns. And that sets us up well for the next chapter, where the footprint becomes less about specialized military technology and more about something depressingly ordinary. Waste that reaches even the deepest places on Earth.
Let's get a hard truth on the table right away, because this is the chapter where the mood changes. The Mariana Trench is not a sealed-off sanctuary. It's remote, yes, but it's not protected by distance in the way people imagine. The deepest place on Earth has already been touched by the most ordinary signature of modern life, our waste. And in some cases, it's not even subtle. It's there as objects, as particles, and as chemicals that never belonged in these ecosystems in the first place. Start with plastic, because the evidence here is straightforward and uncomfortable. Researchers have documented plastic debris in deep-sea trenches, including the Mariana, and microplastics have been found in Hadal organisms. One of the most striking findings from recent decades is that amphipods living at extreme depths have been shown to ingest plastic fibers and fragments. That's the key point for a lecture audience. It's not just that a bag might drift down and land somewhere. The plastics are entering the food web at the bottom of the world. So when we say the trench is a dump, we are not only talking about trash as scenery, we are talking about trash as biology. How does plastic even get down there? This is where the deep sea stops feeling like an isolated abyss and starts acting like a gravitational sink connected to everything above it. Plastics can reach trench depths through several pathways. Some items sink directly once they're weighed down by biofouling or trapped in aggregates of organic matter. Others break apart at the surface into microplastics that hitchhike downward in marine snow. And some are carried by currents until they hit the right topographic trap. That last part matters more than people think.
Trenches are shaped like long, steep collectors. They can concentrate debris the way a valley concentrates runoff after a storm. So the Mariana isn't just passively receiving what falls straight down. It can be actively accumulating what the wider ocean system passes along. There's a psychological trap here that your audience might fall into, and you can gently head it off. People often imagine pollution as a nearshore issue, something that belongs to crowded coasts and industrial bays. The trench story proves that the ocean doesn't respect that boundary. Our waste doesn't stop at the continental shelf. It keeps moving. The deep sea is part of the planet's waste pathway, whether we like that idea or not. Now, widen the lens beyond plastic objects to chemical pollution. Several studies have found surprisingly high levels of persistent organic pollutants in trench animals, including compounds like PCBs and flame retardants. These are industrial-era chemicals that can travel long distances, persist for decades, and accumulate in fatty tissues. The unsettling implication is that even Hadal ecosystems can become reservoirs for contamination that originated thousands of miles away. Again, this is not the deep sea is next to a factory. This is the deep sea is connected to the global circulation of human-made chemistry. So plastic becomes a kind of visible symbol of a larger reality. The trench is downstream from civilization. Now, let's handle the nuclear part carefully, because this topic is easy to sensationalize, and your credibility depends on precision. The strongest, safest way to frame this is not people dumped nuclear waste directly into Challenger Deep. The historical record of ocean dumping of radioactive waste mostly involves specific sites used by various countries during the mid-20th century before international restrictions tightened. That practice was curtailed and eventually banned under evolving international agreements. But even without direct trench dumping, radioactive materials have entered the ocean through other pathways that matter for the big picture. Atmospheric nuclear weapons testing, especially in the mid-20th century, released radionuclides that spread globally. Some of that fallout entered the ocean and became part of the long-term chemical background of marine systems. Add to that accidents and releases from nuclear facilities that have contributed trace signatures to ocean waters. Over time, the deep ocean and its sediments can act as a sink for these materials at low concentrations. So what can we say honestly about the Mariana context? We can say that the trench is not just vulnerable to physical debris, but also to the slow, persistent arrival of trace contaminants from the surface world. If microplastics can reach Hadal animals, and if long-lived industrial pollutants can show up in trench food webs, then it's scientifically reasonable to treat the Hadal zone as part of the endpoint for multiple kinds of human-derived contamination, including radionuclide traces. That doesn't mean the trench is glowing or uniquely radioactive. It means the deep acts like a ledger. Given enough time, it records what the surface puts into circulation. This is a good place to pause in your lecture and let the audience feel the scale of the problem without drowning them in numbers. The Mariana Trench is not polluted in the same way a river next to a chemical plant is polluted. The ethical problem here isn't that the trench is as bad as a surface disaster zone. The ethical problem is that even the most extreme, physically protected places on Earth are still within reach of our global footprint. The trench is a warning about the reach of modern systems. And there's a second layer that's easy to miss. Deep-sea organisms often live slow lives. Growth can be slow. Reproduction can be sporadic, and population turnover can be limited. That means contamination might linger in a way that is harder to detect in short-term studies. It also means recovery from new disturbances could be slow, even if the contamination levels are not dramatic in any single moment. In other words, resilience in the deep is not guaranteed just because the environment looks empty to our eyes. So, how do you land this chapter in a way that sets up what comes next? I'd end with a simple, uncomfortable transition. Once we accept that the trench already receives our unintended waste, we also have to confront the possibility of intended industrial use of the deep-sea floor. That leads directly into the next chapter, the new gold rush of deep-sea mining, where the issue isn't accidental contamination drifting downward, it's deliberate human extraction in one of the least understood living systems on the planet.
This chapter is where you can feel the story pivot from what we accidentally leave behind to what we might intentionally take. And the Mariana Trench sits right in the emotional blast radius of that debate, even when the specific mining target isn't the deepest trench floor itself. Because deep-sea mining is not a single thing. It's three main targets with three different ecological footprints. Polymetallic nodules scattered across abyssal plains, seafloor massive sulfides around hydrothermal systems, and cobalt-rich ferromanganese crusts that grow on the slopes and summits of seamounts. The Marianas region is especially relevant to the crust conversation because volcanic arcs and seamount-rich settings are exactly where you find these hard, metal-rich coatings, typically forming at depths from hundreds of meters down to several thousand meters, with some sources describing their main resource depths roughly in the 600 to 7,000 meter range, and a sweet spot of thicker, richer crusts often shallower than the deepest trenches. So you can say this clearly to your audience. The current industrial interest near the Marianas is less about scooping the bottom of Challenger Deep and more about the broader deep Pacific architecture around it, abyssal plains, seamounts, and the complex belt of habitats that surround the trench system. Now, the gold rush part. The economic driver is the same one you hear in every modern critical minerals conversation. Nickel, cobalt, manganese, copper, and other metals that sit inside batteries, electronics, defense systems, and grid-scale infrastructure. The promise is seductive. Supporters argue that mining the deep sea might reduce pressure on some terrestrial mining frontiers. Critics argue that the deep sea is too poorly understood and too slow to recover for this to be anything except a global-scale gamble. The honest academic position in a lecture like yours is not to caricature either side, but to show why the uncertainty itself is the central political fact. And that uncertainty is still real because the regulatory picture remains unsettled. In international waters, commercial deep-sea mining has not begun, and the International Seabed Authority is still negotiating the exploitation rules that would govern any future large-scale operations. Talks continued through July 2025, with further negotiations expected to continue afterward. At the same time, exploration activity is already substantial. As of 2025, the ISA had issued about 30 exploration contracts across nodules, sulfides,
and cobalt-rich crusts, sponsored by roughly 20 countries. That's an important nuance. The deep-sea mining future is not hypothetical in the sense of nobody is involved. The groundwork is already laid. The pressure is building. The other reason this chapter feels newly urgent for a U.S. audience in late 2025 is that there are now specific domestic policy moves in the Pacific. The Bureau of Ocean Energy Management announced and then published a request for information and interest for potential commercial leasing of seabed critical minerals offshore the Commonwealth of the Northern Mariana Islands, with the Federal Register notice dated November 12, 2025, and a 30-day public comment period closing December 12, 2025. This is an early step, not a decision to lease, but the geography matters. The RFI area is described as east of the Mariana Trench National Monument along the edge of the U.S. EEZ, covering a very large area with depths roughly from about 1,130 to 7,650 meters and including abyssal plains and seamount features. In a lecture, that's a powerful moment of specificity. It tells the audience that the new gold rush is not only an international law story far away in conference rooms, it is also a local Pacific governance story unfolding near communities that depend on healthy ocean systems for fisheries, culture, and economy. Now we need the ecological core, because otherwise this chapter turns into just policy. The strongest evidence we have for risk comes from disturbance experiments and test sites associated with nodule environments, especially in the Clarion-Clipperton zone. A key result that has become hard to ignore is that physical impacts from past test mining can remain visible and biologically meaningful for decades. Studies linked to older disturbance sites have found that some communities remain altered long after the original tracks were made, with slow or incomplete recovery for certain larger habitat-forming organisms that depend on nodules as hard substrate. This is not just a scary headline. It's a straightforward ecological logic problem. Polymetallic nodules grow extremely slowly on geological timescales. If your habitat is a field of nodules and the nodules are removed, you've lost the basic architecture of your ecosystem for a time period that effectively exceeds human planning horizons. And even when we switch from nodules to cobalt-rich crusts, the concern remains structurally similar. Crusts are also slow-growing mineral surfaces that function as both resource and habitat on seamounts. Removing them is not like trimming a renewable crop. It's more like shaving off a living neighborhood's foundation. So the big worry isn't only we might kill some individual animals. It's we might restructure entire benthic communities for generations. There's another layer of risk that is newer in the public argument and very relevant for a big picture lecture. Mining doesn't only disturb the seafloor, it can generate sediment plumes, noise, and light in an environment that evolved without all three at industrial scales. Recent research has also raised concerns about mid-water waste discharge, suggesting that ocean food webs could be affected if nutritionally poor mining particles dilute or replace natural organic particles for zooplankton and other particle feeders. That's a reminder that deep-sea mining might not stay neatly confined to the bottom. The consequences could spread upward through the water column. So where does that leave us in the Mariana-specific story? It gives you a clean, balanced, but not wishy-washy conclusion to say out loud. The Mariana Trench region represents a unique convergence of geology, biodiversity, and cultural and strategic importance. Mining interests focusing on the broader deep-sea landscapes near the monument raise a question that's bigger than any single permit or company. Can we build a critical minerals future without repeating the old pattern of treating remote environments as expendable because they're out of sight? The science so far suggests deep-sea disturbance can be long-lived and that our predictive models are still incomplete. That doesn't automatically answer every policy question, but it does justify caution at the scale that industrial mining would require. And that's a strong bridge into the final chapter of your outline, where the trench becomes not just a place of earthbound controversy, but also a scientific analog for the search for life in icy moons. Because how we study the deep responsibly on Earth may shape how we imagine exploration ethics beyond Earth, too.
This last chapter is where the Mariana Trench stops being only a story about Earth and becomes a training ground for how we think about life elsewhere. And I want to be careful with the tone here, because it's easy to slip into sci-fi excitement and accidentally oversell what we know. The honest claim is not the trench proves there's life on Europa or Enceladus. The honest claim is that the trench helps us practice the right questions. Europa, a moon of Jupiter, almost certainly has a global subsurface ocean beneath an icy shell, inferred from multiple lines of evidence, including magnetic and geological indicators. Enceladus, a moon of Saturn, has strong evidence for an internal ocean too, and the game-changing observation there was the plume activity from the South Polar region, sampled by the Cassini mission, which detected water vapor, ice grains, salts, and organic compounds. Later analyses also pointed to molecular hydrogen in the plume, which is particularly interesting because on Earth, hydrogen can be a sign of water-rock reactions that feed chemosynthetic ecosystems. So the astrobiology excitement around these moons isn't a random wish. It's tied to real chemistry and real physics. But now, bring it back to the Mariana Trench. What does the trench offer as an analog? 3 big things. First, it gives us a real-world laboratory for life under extreme pressure and permanent darkness. The Hadal zone is not identical to an alien ocean, but it is one of the closest environments we can study on Earth where sunlight is irrelevant and where life has to make a living without the surface energy economy. That matters because the big astrobiology argument for Europa and Enceladus hinges on chemosynthesis and chemical gradients rather than photosynthesis. When we study trench microbes, trench scavengers, and the broader deep-sea chemosynthetic story, we're testing a basic principle. Can stable ecosystems exist when the primary energy source is geochemical rather than solar? On Earth, the answer is yes in specific environments. So the trench strengthens the plausibility framework, even if it doesn't give us a direct prediction of what specific species would exist elsewhere. Second, the trench helps us understand how topography shapes deep ecosystems. This is an underappreciated point outside specialist circles. We tend to imagine deep oceans as uniform, dark volumes. But the Mariana system shows how canyon-like geometry can concentrate organic matter, how basins can become collectors, how slopes feed material into deeper pockets. That's relevant to icy moons because those oceans might also have complex seafloor landscapes with ridges, vents, and chemical hotspots.
If we someday explore a European ocean, success may depend on finding the right ecological addresses rather than sampling randomly. The trench is a reminder that in the deep, location matters, even when everything looks equally black from a distance. Third, this is the part that ties science to engineering and to ethics. The trench teaches us how hard it is to access a high-pressure ocean responsibly. The tools we build for Challenger Deep, pressure housings, autonomous landers, long-duration sensors, careful sampling protocols, are conceptually similar to what we would need for an ice-penetrating mission and an under-ice autonomous explorer on Europa or Enceladus. Not the same hardware, but the same design philosophy. Minimal failure points, extreme redundancy, patient data collection, and a deep respect for unknown environments. The trench also helps us rehearse planetary protection thinking. Even on Earth, we struggle with the idea that remote, deep habitats can be affected by what we drop, lose, or dump. If we can't fully protect the deepest ecosystems here from plastic fibers and persistent pollutants, that should humble us about how carefully we must approach an ocean on another world. The ethical lesson is transferable. Once you can reach an extreme environment, the risk is not only discovery, the risk is contamination, disruption, and leaving a footprint you don't fully understand. Now, let's do a quick reality check so this chapter stays academically grounded. The Mariana Trench is still an Earth environment with Earth biology. The energy sources in the trench include detrital input from the surface ocean, and in places across the broader Mariana region, geological activity that can support chemosynthetic systems. On Europa and Enceladus, the surface-ocean link would be very different. There might be no marine snow in the Earth sense, because there's no photosynthetic surface ecosystem feeding the depths. So the analog is stronger for the chemosynthesis logic than it is for the full food web architecture. That distinction is worth saying out loud in your lecture. It makes you sound careful, and it's the truth. Another limit is timescale. Earth's deep biosphere has had billions of years of biological continuity and evolutionary experimentation. Icy moons may have had long-lived oceans, but we don't know their exact histories of chemical stability, heat flow, or the availability of key elements. The trench doesn't solve those uncertainties. It just gives us a practical demonstration that life can be robust in darkness with chemical energy, and that ecosystems can be stable in extreme pressure regimes. So the trench functions as an argument of plausibility, not proof. If you want to bring this to a crisp ending for your audience, you can frame it like this. The Mariana Trench is Earth's best classroom for learning how to ask astrobiology questions responsibly. It teaches us that habitable doesn't have to mean sunlit. It teaches us that the deep is not uniform. It is structured. It is patchy. It is shaped by geology and chemistry. And it teaches us that the engineering required to visit an extreme ocean is inseparable from the ethical responsibility of what we might leave behind. That's a strong final note to Part 4 and to the whole lecture arc of your outline, because it brings the story full circle. We started with the idea that our planet has a forgotten frontier. We end with the idea that understanding that frontier may shape how we search for life beyond Earth, and how carefully we choose to do it. Thank you so much for watching our video and supporting our channel. See you in the next episodes, and good night.